Hello friends, today I'm going to solve LeetCode problem number 1579. Remove max number of edges to keep graph fully traversable. In this problem, we are given an undirected graph of n number of edges, and there are two entities, Bob and Alice, and there are three types of edges in the graph. Now, on type 1 edge on the graph, only Alice can traverse, and on type 2 edge, only Bob will be able to traverse, and on type 3, both Alice and Bob will be able to traverse. Now we are given an array of edges of the graph, and then each of the edge has a type and the nodes from between which the traversal could be made, and the edge is bidirectional, which means that you could traverse from UI to VI or from VI to UI. Now we need to make sure that Alice and Bob can traverse all of the edges. That is, Alice and Bob can reach all of the nodes, which means that the graph is fully traversable. So now we will be removing few edges from the graph and minimize the number of edges in the graph. That is, we will be maximizing the number of edges which we can remove from the graph, and even after that the graph should be fully traversable by Alice and Bob. So we are going to maximize the number of edges we can remove so that the graph is still traversable, fully traversable. Else, if we are not able to if Alice and Bob are not able to traverse the graph at all, then we are going to return -1. Now let's see how we could solve this problem using this example first. So we are given this example here. All right, now type 1 is the type which is traversable by Alice, type 2 by Bob, and type 3 by both Alice and Bob. All right, I'm gonna use a different color for Bob. So type 2 is by Bob and type 3 is by both Alice and Bob. Now let's see in this graph. So we need to remove edges such that the graph is still fully traversable. That is, we are going to maximize the number of removals. That means that we are going to minimize the number of edges in the graph. So let's just first look at this edge here, edge between 1 and 2. What are the types of edges between 1 and 2? Well, one is a type A1 and the other is a type 3. That is, Alice can traverse from this edge, and again Alice can traverse from this edge as well, right? So isn't it redundant to have this edge here? So we are just going to remove that edge because that's a redundant edge. Now we still have type 3 edge, right? Which means that Alice can traverse from this edge. Also Bob can traverse from this edge. So basically Bob and Alice can reach node 1 and 2 from any of these using this edge, right? Now can Alice reach node 3? Let's see. So if Alice can reach node 1, Alice can reach node 3 because this is of type 1. And also if Alice can reach node 2, then Alice can reach node 3, right? Because it is of type 3. So basically we know that Alice can reach 1 and 2, so Alice is able to reach 3, right? But do you think like we need 2 of these nodes? We don't need to, right? We are going to minimize the number of nodes. So which is the node that we could remove? If we remove this, let's see what happens. Let's check for Bob. So is Bob able to reach node 3 if we remove this node? Well, let's see. If from node 2 Bob is not able to directly reach node 3, right, because we removed this edge. And what about from node 1? Only there is a type 1 connection between 1 and 3, so Bob is not able to reach node 3, right? Now is Bob able to reach node 4? No, because again this is a type 1, right? So Bob is not able to reach node 4, but from 4 Bob is able to reach node 3, right? So what happens if we remove this node, this edge? If we remove this edge, we know that Alice can reach node 3 from node 2, right? So Alice is still able to traverse 1, 2 and 3. We know Bob is able to traverse 1 and 2. Now is Bob able to traverse 3? Yes, from 2 it could traverse to 3 because this is a type 3 edge, right? So if we look carefully, we will notice that removing edge of type 3 doesn't help us, right? Because either one of these two edges, basically removing type 3 is not a good idea. And the next thing is that we should prioritize removing type 1 and type 2. So we should prioritize removing these two edges. Why? Because we want to remove maximum number of edges, right? So if let's suppose here we have a graph, right? We have a graph here, okay, and there is an edge between these two, okay, that is of type 2 because it's green. This is of type 3 because it's red. All right, and we have a type 1, red is type 1, okay, and now we have a type 3. This is type 3, okay. So we have these graphs here. Now which edge would you remove from these graph? Are you going to remove this edge? If you remove this edge, then you would need, if you remove this, okay, let me just modify this example. Yeah, let's just keep it this much. Okay, simple. Now we know that this node 1 and node 2, okay, and this would be node 3. We know that from node 1 and node 2 both A and B can traverse, right? Node 1 and 2. Now what about 3? So A and B is able to traverse, right? A can traverse from this edge, B can traverse from this edge. Now if we remove this edge, then we'll have to keep both of these edges, right? Red one, type 1 and type 2, because only A can traverse from type 1, only B can traverse from type 2. But instead of removing type 3 edge, okay, instead of removing the type 3 edge, what we could do is we could remove type 1 and type 2 edge. So now we remove two of these edges, and then the edge we have is type 3, and both Alice and Bob can use this edge, right? So with type 3, Alice and Bob are able to traverse all of these nodes. So to maximize the number of node removal, we are going to remove type 1 and type 2, prioritize removal of type 1 and type 2, and that is how we are going to solve this problem. Now let's see the time complexity. What would the time complexity be? Okay, let's suppose if there are n number of edges, then for that, every time we remove an edge, okay, every time we remove an edge, we are going to check if A is able to traverse, Alice is able to traverse the whole graph, and if is Bob able to traverse the whole graph. And what happens in that case is, if there are n number of edges, and we are checking for each edge, we are checking if Alice is able to traverse the whole graph, which means we are trying to traverse the whole graph. So that would be n times, right? N times for each of the traversal, which means we are performing n number of removal. Then that would be n times n time complexity, right? N times n for Alice and for Bob. This would lead to time limit exceed. So we are not going to do it in this way. We are actually not going to remove the graph, remove the node we are going to perform a reverse operation. That is, we are going to add nodes to our graph, add edges to our graph. Okay, so what are we going to do is we are going to start just from the edges. So let's suppose there we have 1 2 3 4. Okay, this is the same graph. Now we will prioritize, since we were removing here, we prioritize the removal of type 1 and type 2, right? Now since we are adding, we'll prioritize the addition of type 3. Okay, so now we check for the ages. Okay, since we are given the ages array, so we'll check for those ages which are of type 3. So this is type 3 and we have an age between 1 and 2. So we'll try to connect the age between 1 and 2 with type 3 connection. Okay, so we'll connect 1 and 2. Since it is not connected, we connect it with an age. Now the next age we are given is, okay, I'll just copy this and paste it here. The next age we have is 3, type 3 between 2 and 3. Okay, so between 2 and 3 we do not have any connection, right? So we connect this 2 and 3. Now is there any other type 3 age? No, right? So we are done with these two type 3 ages. Now we are going to go with either type 1 and type 2. So now we have a type 1 age which is between 1 and 3. So let's use red color. So between 1 and 3. Now 1 and 3, 1 and 3, we can see that 1 is connected with 3 via this age, right? Via 2. So is it necessary for us to connect it? No, because A and B both are able to traverse 1 and 3 with this route, right? So we won't be adding this to our age at all, to our graph. Now let's look at this type 1 age between 2 and 4. Do we need this age between 2 and 4? If we look at this is a disconnected graph and 4 is a disconnected graph, right? So we need to connect these two. Now since this is connected, we have LS is able to traverse the whole tree. Now what about this again, between type 1 between 1 and 2? Do we need 1 and 2? No, because it's already connected, right? Now we have a type 2 between 3 and 4. Do we need a 3 and 4 connection? If we only look for Bob is able to traverse 1 2 3. Bob is not able to traverse 4 because it is disconnected. So for Bob we will have to connect this, right? So now we have a connected graph where both Alice and Bob can traverse. So this is how our graph will be. So to perform this operation, we are actually going to use UnionFind method. So what is UnionFind? I have just created an algorithm for it. It's basically a data structure. So okay, let me just explain it to you first here. So what we did here was, first of all, we had all the ages disconnected, right? So age 1 was age 2, age 3, okay, not ages but nodes. We have all the disconnected nodes, right? Initially there was no connection between all of these nodes. So the parent of each of these nodes are them itself. Now what happens next is, when we perform a connection, we are going to check if the parent of both of them are same or not. That is, we are going to perform a union operation. To perform that union operation, we are going to find the parent of both the nodes that we are performing the operation on. The nodes are 1 and 2. So we find the parent of node 1 and node 2. Since the parent of both node 1 and 2 are different, that is, parent of 1 is 1, parent of 2 is 2. So what we do is we connect the two nodes with an edge and then we change the parent. Okay, initially parent of 1 was 1, parent of 2 was 2. Now we change the parent of one of them to Okay, so what are we going to do is we change the parent of 1 to 2 here. Why? Because like the number of nodes initially in this graph when they were disconnected was 1, when this was disconnected was also 1. Now when they are connected, the number of nodes is equals to 2, but that's not the case. Why we wrote here 2. Okay, I'll just let you know in a while. You will just get to know in a while. Now let's see 2 and 3. Okay, so when we connect, when we are trying to see 3 has a parent 3, 4 has a parent 4. Okay, so the parent of 2 is 2, parent of 3 is 3. So we are able to perform union operation because these are separate. So we connect them, and now we have to change the parent of either 2 or 3. So what are we going to choose? Actually, we are going to choose to change the parent of 3 because it only had one node, right? One node and this had two nodes in it. So if we were to change the parent of this to 3, then we had to change the parent of both of these nodes, right? But if we are changing only parent of this node, that we only have to change one node, right? So that is why we keep track of the number of nodes in each of the connected graph, so that we could change the number of nodes, assign the parent. So now we have assigned the parent of 3 to 2. So all of these has the same parent. 4 still has a different parent, right? So now when we are able to, where we try to connect type 1 with node 1 and 3, we see that 1 has a parent of 2, 3 has a parent of 2. Since the parent is same, that would mean that they are connected, so we don't perform a union operation now between h2 and 4. So h2 and h4, they are not connected, right? Because they have different parent. h2 has 2, h4 has 4. So what we do here is we perform a union operation now, and we connect. Now we change the parent. So now parent of 4 becomes equals to 2. Okay, so parent of 4 becomes equals to 2. All right, and similar with this one, 1 and 2, both of them have the same parent, so we are not going to perform union. Now what about this 3 and 4? They still have the same parent, right? Which means that we wouldn't connect them. But earlier we saw that we connected this with a green edge, right? That is with type 2, because B was not able to traverse it. So here actually we are going to create two different graphs, one for Alice, one for Bob. So this one is for Alice because we have the the type 3 nodes and type 3 edge and type 1 edge. Now for Bob we are going to create the same. So we'll have edge. Okay, I'm just going to use green. So we have 1, 2, 3 and 4. And similar to the one that we did here, we are going to do the same thing, that is attach node with edges of type 2, type 3. Now in case of no edges of type 1, we are not going to perform anything for Bob, but for type 2 we are going to perform, right, operation. So when we check 3, 4 are not connected. 3 has a parent 2, 4 will have a parent of 4. Since the parent are different, we perform the union and we connect this. Now we could see like Bob is able to traverse all of the nodes, and also Alice is able to traverse from all of the nodes, right? So this is how we are going to perform the union operation. So if you look here, we have the rank, which will keep the size of the graph connected so far, and the parent array, which is the parent. Now we create a constructor where the rank of all of them is equals to 0. We could also initialize this to 1, and then parent of all of the nodes is the node itself. Now we find the parent of each of the node, And then here in the union operation we are performing the union. So we are performing the union only if the parent is not equal. If the parent is equal, we return 0. If the parent is not equal, then we perform the union based on the rank. That is, if the rank, the number of connected edge is greater in this graph, then we change the parent to that one, else we do this. Okay, now here for maximum number of edges to remove, we create two different instances of UnionFind, one for Alice and one for Bob, because we saw here, right, we saw that we have to create two different instances here, right? So we create two different instances. We also create three variables, one for Alice edges, Bob edges, and redundant edges. So this will be the number of edges in Alice, in Bob graph, and this is the number of edges that we'll be removing. Now here we are going to prioritize the age 3, right, as I already told. So for in this for loop we are just going to perform operation for age 3. So if age is type is equals to 3, then we check, we perform the union operation. We check if we could perform the union. If we are able to perform the union, we increase the number of edges in both Alice and Bob, right, because we are connecting two nodes, that is age is increased by 1. If we are not performing the union operation, that is this age is redundant, we didn't connect the two nodes, right? So the age is redundant, so we are increasing the number of redundant age, that is the age to be removed. Similarly, now here once we have done for age 3, we are going to do the same thing for ages 1 and age of type 2. So we compare, if it is of age 1, that we are only going to do it for Alice. So we, if we are able to perform the union, we increase the number of nodes for Alice, else we increase the number of redundant edges, similar for Bob, and then finally we return if the ages in Alice is n-1 and Bob is n-1, then we return the redundant edges. If we say that we are not able to return, both Alice and Bob are not able to traverse, and hence we return -1. So why are we checking it for n-1 and n-1? Because if there are n number of nodes, then we need at least n-1 edges, so that all the nodes are connected, fully connected, right? If you see here, we have 4 nodes and then 3 edges, that makes this graph fully traversable, right? Similarly in this case, so that is why we are comparing it with n-1 and then returning redundant edges. So that's all for this problem. Talking about the time complexity here, so we are performing, and we have n number of nodes and we have some number of edges, right? Let it be e number of edges. So we have a for loop here and a for loop here, so that would be O of e time complexity. Now since for each of the edge we are performing a union operation, right, and here we are calling this function, and this, in this function we are calling our find parent, and find parent is basically it could deepen along with, you know, the number of edges, growing number of edges. So in that case that would be alpha of let's keep it the value k. Okay, so that would be O of e alpha k. All right, time complexity and the space complexity would be so the space complexity would be, yes, here since we are using a parent array and a rank array, and these each are storing the number of nodes, right? So that is why n space complexity would be O of n. Okay, so that is all about this problem. Hope you like my solution. Let me know in the comments down below if you have any problems, any questions, and don't forget to like and subscribe to my channel. Thank you so much for watching till the end.